Okay, in this problem, it's 1 degree of freedom, because if you stop, part A is moving. If you stop A, then it fixes the rod AB. If AB is fixed, D is fixed. And if D is fixed, then C can't move either. So it's 1 degree of freedom. Because you are giving me one velocity, I can therefore find all of the velocities that you want. And what you want is you want the velocity, and you also want the acceleration of this guy up here, B, this round B. And therefore, I know that I can do it, and I do not need a free body diagram. As usual, we take our i's and j's to the right. Doesn't really matter, I just like to be consistent. And so I'm going to use vector loops. One thing to watch out for is the units. The distances are millimeters. I'm going to use millimeters. And then when I use this number here, I'm going to recognize that it's in meters. So be careful of that. The other thing that's unusual about this, well, we'll get to it when we get in there. Okay. So I think that when I look at this, it looks to me like there is maybe the easiest thing to do is to use vector loops. And after I solved it, I found a loop that was probably a little bit easier. We'll cover that later. But the first thing I saw was this blue loop that I'm pointing out here. Between C is a special point, B and A are special points, B is also a special point. So between these points I saw a C to D, down to A, and then back over to C. So I saw that loop. That's the blue loop, the equation that I wrote here. And the other thing to watch out for is when you're writing loops, you know that you're going to take derivatives. So these things like 30 degrees in here, you do not want to plug your loop in as 30 degrees because you cannot put numbers in, constants, until after you take a derivative. Same thing up here with this 3, 4, 5 triangle. I'm going to use that, but not until after I take the derivatives. Otherwise, I'll end up not getting the correct derivative. Okay, so with those things in mind, I start writing a loop. It doesn't matter where you start, but I'm going to start over here at C, and then I'm going to go from C to D, D to A, and then, if you notice, I'm going to come down a distance right here, and then once I get to A, I'm going to put down a distance, and we call that Y, and then that puts me down here at this dotted blue line, and then I'm going to go from the center line, where point A is, and I'm going to go all the way back over to C. So that's how I'm going to write my loop. Alright, so the first thing is I'm going to go 400 millimeters. Up here, 400. When you go from C to D, you're going to go to the right. So that's a positive I. That's right. And the distance is the cosine of this angle theta. And I'll put it in as, and then after I take derivatives, I'm going to say that theta is equal to 30. Okay, so I'm going to go to for the horizontal distance, it's a cosine. And then the vertical is going to give me the sine, and that puts me at D. So if I go a distance in blue here, this distance, I'm going to be standing on point D. And then to go from D down to A, I'm going to go to the right, and I'm going to go down. The magnitude is 300, right? So it's 300 millimeters. To the right is positive I, and then down is minus J. And so if you look at the angle, where I've defined beta, right, and eventually beta is going to be this 3, 4, 5 triangle here. But I'm going to go, the horizontal distance is, with this triangle here, the horizontal distance is the cosine of beta. The vertical distance is the sine. Okay, so now after I've done that, I'm standing at point A. I'm going to go down the center line until I get to this little yellow dot here. That means I'm going to go down, negative J, and the distance is this variable Y. Okay, and then I'm going to go from the center line all the way back to point C. So that means left, so that's a negative I. And the distance is X, right, which is also a variable. That's equal to 0. Then what I did, I'm circling in red the variables. So theta is a variable, beta is a variable. For derivatives, y is a variable, that's changing, and so is x. So I have 4 variables. So I know that when I take a derivative, those 4 circled variables are going to end up with derivatives or dots on them. If I use Mathematica, they'll be ticks, but anyway, they're the derivatives. So that's 4 of these things. Now, one of them is going to be known. That's going to be the velocity of A. But that leaves me with 3 that I need to solve for. Well, I only get 2 equations for a 2-dimensional vector loop, so I know I'm missing something. Plus the fact that I know I'm missing something because none of these distances tell me anything about where the block B is. So if I put 2 and 2 together, I say, oh, I must be missing another loop. Okay, and this will happen to you every now and then because you end up with too many variables. And so that told me to go look for another loop. There's probably an easier one in here, but I'm going to go from, let's say I'm going to do the red ones I circled. Okay, so I'm going to go from C to D to B, and then what I'm going to do is I'm going to drop straight down from B until I hit this center line, right? That's a constant distance, if you notice. And then I'm going to go from that center line, from that point, back over to C, and I'm going to call that XB for the, the distance of B. Okay? All right, so now the problem, the only thing else, the only complication here is this distance XB, you might think, oh, that's the velocity, or when you take the derivative of it, is the but it's not, because this guy, XB, is actually being measured from a moving point. So when I take the derivative, that's not going to be the velocity of B. So to try to make my point here, what I've done is I've drawn, because velocities need to be measured from a fixed reference point. So here I'm drawing a fixed horizontal line right there. See that little blue dotted line? That line is right through the center line of this slot. And any fixed point would be good. But I use that one because I've got this variable x. I'll just repeat it up here. So that x and this x down here, they're the same. And I'm just trying to show, just kind of pulling it out of the figure so you can see it better. It's measured from this fixed dotted line right here. And that goes over to point C. And that's a variable, but it's measured from a fixed point. And then the XB goes from this dotted line, which is the location of where C is, back over to B. So what I'm doing here is I'm saying that the position of B from a fixed point, it's first of all I'm going to go left, right? So I'm going to go left, negative I, a distance of x, and then I'm going to come back to the right, right? To the right is a positive I, a distance xb. And that is the position of B. So if I differentiate this equation, then I'll have the velocity of B, right? So that's the only other odd thing that's happening. But let's get the red vector loop in there. And like I said, there's multiple loops, so maybe you would want to go from A to B to straight down and back over to A. Whatever makes sense to you, you can do. There's multiple ways of doing it. Okay, so I'm going to go from C to B. From C to D, that's a distance of 400. It's to the right. If you notice, you're going from C to D, you're going to go right. So it's a positive I. And then you're going to go up. Positive, J is up. The distances are cosine of theta in the horizontal and sine theta in the vertical. That puts you at D. Then I'm going to go from D to B. So I'm going to go left. So that's a negative I. I'm going to go up. That's a positive J. And the distances, avoid the 3, 4, 5 triangles. So the distances are going to be cosine of beta in the horizontal. Remember, I'm going from D to B. And the sine of beta in the vertical. And of course, the distance is 250. Now that you're at B, I'm going to drop down from B to the center line of C. That's a constant, so it's down, so it's a negative J, and it's a constant. So I'm just going to call it C. And then once you're standing there at that center line, you're going to walk back to the left. So left is a negative I. And the distance, I'm calling it XB. So that's the distance XB. And since you're back to the where you started with, that's equal to 0. Okay, so to finish this vector loop, I'm going to go to the Mathematica, which I'll do in just a second. It was also asked for me to do this with special points, so I did that. And when you're doing special points now, so here are the special point equations. The first thing is to find out how many bodies there are. There happens to be 2 bodies. Pretty obvious. And then you want to locate the special points on each of the bodies. So for body CE, there are 2 special points. One is C, because you know something about it. It's moving horizontally. It's also, you could say it's touching the body CE and also that slot. Whatever. D is special because it is touching more than one body. So on that CE body, there's 2 special points. That means you're going to write 1 special point equation. For the other rod, AB, there are 3 special points. You have A, you have B, and you have D. So that is 3 special points on that body. So I'm going to expect to write 2 equations. So let's see what I'm doing down here. So you want to write the velocity equations first. In this case, you have to, because you want to find the velocities. And so the first equation that I'm writing between C and D, that's on this rod, CDE. If you notice, like we said, there were only 2 special points on that body, and therefore there's only 1 special point equation that you're going to write between C and D. Okay? So if you look at this, it doesn't matter which, I'm going to write it between C and D. It doesn't really matter if you start with C or with D, so just pick, take your pick. I chose D to put on the left-hand side, right? So you have D on the left. That was arbitrary. C is the other point that you're writing it between. You don't have much choice there because there's only the 2 points on it. The omega is always, this omega in the equation is always the body that C and D share. And the body that they share is this link right here, which I'm calling CE, right? So that would be the angular velocity of CE. You don't really know. You can spend and waste time trying to figure out which way the thing is rotating. It doesn't really matter because you're going to solve for the angular velocity. And because you're going to solve for the angular velocity, you can put it in there any direction you want, and a positive says you did it right. I'm going to assume that it's counterclockwise, so I put it in as a positive omega k. And then you cross it with the r vector. The r must go always from the whatever point is here on the right-hand side to the other one. So it has to go from C to D. No choice about that. Okay, here is the special point equation between A and D. I arbitrarily chose A and D. You could have gone from A to B directly, whichever one you want. And then here's the second equation, the special point equation for that body. And again, the omega is the body that they share. The R, once you determine which of these A's and D's you put on the right and left-hand side, that one gets fixed. Okay, so while we're at it, we're going to go ahead and write down the position vectors. So the R from C to D is given by this right here. And notice I'm using 30 degrees. It's because you don't take a derivative of the special point equations. And so you can put in constant values, or the values that they are right now. So that's from C to D. And from A to D is going to be left and up. And I'm using the 3, 4, 5 triangle. So it's left, that's a negative I. Up is positive J. And then from B to D is right and down. So it's a positive I. Down is negative J. And again, 3, 4, 5 triangles for that. Okay? Then while you're at it, you want to write the acceleration. So you basically mimic it. So this equation matches this one. The middle equation, in a sense, matches this one. And then the bottom equation matches the bottom one. So if you notice, the top one was D and C, so this one's D and C. This was omega CE. This one ends up being alpha CE. Same R's. And the omegas come from the velocity equation. So that's how I'm going to write these, and then I'm going to go to the Mathematica file and show you how that works. Okay, so here's the Mathematica file, and this stuff here is the standard thing that I use to manage handling vectors. And then this section is the kind of typical sort of stuff that I'm doing the loop equation first, where I just define, to simplify typing. So th is theta, beta is beta, the lowercase y is the values y. So these are just the variables that I'm putting in that I talked about in the other one. The xb is a variable, and then I have cosine of theta, sine of theta, cosine beta, sine of beta to make the typing easier. And then you execute that. Then here comes your loop equation. So here's the two loop equations that I had. So here's the first one. So it's 400 cosine I sine theta j. So I think these are fairly self-explanatory. But that's the loop equation that comes off of this this one here. So loop equations right there. So this blue loop equation is the first one. The red loop equation is the second one. And so let's go back to the Mathematica. So this is the first loop equation. Here's the second loop equation. The only thing you have to watch out for, but you have to do this for all the time. Since you're writing this as vectors, you need to, when you write 0, you need to say 0i, or you could say 0j or 0k, but you've got to be able to say it's a 0 vector, otherwise it won't put in 0, 0, 0 right here. It'll only put in 1, 0. And then it kind of messes up trying to solve the vector. Okay, so same thing here. So the 0i gives you the 0, 0, 0, 0i gives you 0, 0, 0 there. Okay, so that's your loop equation, and what do you do with it? You take two derivatives. You only take one if that's all you want is velocity. But this is the derivative of the loop, and here's the derivative of the loop. That's the second derivative. All right, and they're ugly. Ordinarily, when I actually do this, I don't bother to print it because it just who cares, right? But anyway, if you notice in here, the four variables that I had that were defined up here, right? Theta, beta, x, y, xb, so I guess 5 variables. Those show up as ticks, and that's what you would expect. So here's a tick, 1, 2, 3, 4, and xb, 6, 5. Those are 5 ticks. So, and then for the second derivative, this is really bad, but notice there should be 5 double ticks. Occasionally, one of these two, there's 1, there's 2, there's 3, let's see, y, 4, let's have 2 double ticks. Here's W, so 5. So there's the 5 guys up there and 5 down here. Now, you have two loop equations, so there's really 4 equations. There's i's equal i's for the first loop, right? All the i's equal to 0, all the j's equal to 0. That's 2 equations. And then for the second loop, i's equal to 0, j's equal to 0. That's another 2. So you're going to have 4 equations, and there's 5 variables. Because one of the variables has to be given, because it's 1 degree of freedom, right? So what you do with the loop equations, after you've taken the derivative, you solve them. So you're going to solve the loop equations. This is the vector solve. And you say, I want to solve the first derivative of the loop. And I'm going to solve for which 4 of the 5 ticks. I want theta tick, beta tick, xb tick, and x tick. So I want you to solve for those guys. And it comes out fairly simple. These are linear equations, so actually solving the derivatives and the accelerations are fairly simple. So it's telling me, okay, theta tick, theta dot is this expression right here. Okay, theta dot, etc. So I have the values, and if you notice, the only thing that's in here that is not known is y tick, right? Y dot. there's a y dot, there's a y dot. That's because you have to know that particular value. So I'm going to put in those numbers here in a second. And then what do you do with the acceleration? The double dot, you solve for the same 4 dot terms that you did before. So you solve for those guys. In this particular case, this expression right here with the divide period, that's how you tell Mathematica to take VANS, that's the velocity answer that it already has. If you want to substitute after it solves it, you want to substitute the velocity answer into the expression. Because what you do is you get the single dot or the single ticks out of the velocity equation. Once you have those, everywhere you have a single tick, you're going to put in the velocity answer. So if you notice in here, when I solved it, the double dot terms have no single dots except the one that is an input. So you have the velocity of that slider. You also have the acceleration of the slider. There are no other ticks in here. Okay, so you've got basically answers. I'm going to put in some numbers. So now that all the taking derivatives is over, I'm going to put in some numbers. Okay, so these are the numbers I'm putting in. Theta is 30 degrees. Beta is the inverse tangent of 4/3, right? So I think that's about 50, 60 degrees, 36. I'm not sure what it is, but it's just an angle that you can put in there. You can do that in the calculator if you want. This value, y tick, that was given. Okay, it said it was moving down at 6 meters per second. So let's go back over there and just take a look at that so you can see what I mean by that. Okay, so this y distance right here, this y distance is the velocity of A, because it's measured from a fixed point, right, from a fixed reference line, and so that's equal to the velocity of A. Now, if A is moving downward, y dot, if A is moving down, like it says, y is getting smaller. If y is getting smaller, y dot is a negative number. So what I'm going to put in there is the number 6, and I'm going to say that it's going down, so y dot is negative. Okay, so let's go back over to the math file, and you can see what I did. I put in a negative for the y dot. I don't believe, was I told the acceleration? I'm not sure that it was. Okay, so if you want me to find the acceleration, you have to give me one. So I'm not sure if the author was asking for it. So I'm going to say that, y, the acceleration of A is, we'll say, up at 3. Okay, so if that's the case, because if you want me to find the acceleration, you're going to have to give me one. Let's see. So we'll go back to the math. And that's what I put in here, positive 3. So I said it was accelerating upward. Okay, so if you put those numbers in, and again, this is the way you tell Mathematica to put in numbers. So in the velocity equation, put in these numbers, and give it to me as a decimal, right? So, because otherwise it gives it to you as these odd fractions, and it's just difficult to compare one answer to another. And so here's the response. Theta dot is a negative 0.7. So since theta dot is negative, theta is getting smaller, which means that rod is actually rotating clockwise. The beta dot is a positive number, so beta is getting bigger. If beta is getting bigger, I'll show you the diagram. If theta is getting smaller, then this guy is rotating clockwise. If beta is getting bigger, then this one is going clockwise. So they're both going clockwise. One is getting smaller, the other is getting bigger. Okay. So those are the answers there. X tick is positive. So XB tick, XB is moving. Well, the distance between C and B is getting larger. The distance X tick, that's the distance from that center line of let me show you. That's between Okay, so x is the distance between A and C, and that one is getting smaller. So C is obviously coming to the right. The distance between B and C is getting bigger, right? So let's go back over and look at the math file and see what the results are. Okay, so the distance between C and B is getting larger. C is moving to the right because x tick is negative, right? The velocity of B isn't, we talked about that. It has to be measured from a fixed point. So the velocity of B is actually a negative x dot plus xb dot. So if you add those guys, xb dot minus xb, x tick, and then for the acceleration it'd be the doubles, right? And you plug in the answers and the numbers. This is what you get for the velocity, and then the acceleration would be that value. Okay, now if you're going to use special points, we should get the same answer. Now we're going to use special points. When I use special points, I like to type in the stuff that I know ahead of time. So I know that the velocity of A is 6,000 and it's going down, so it's a negative j. The velocity of B, I don't know much about it, but I do know that it is horizontal. Okay, I don't know if it's going to the right or left. If I don't know, I assume it's to the right. Velocity of C, similar. Velocity of C is to the right. I have no idea what it's doing actually, but I say I know it is horizontal. The D, I don't know much about it. I don't know anything about it actually. So it has two components, an I, possibly an I and a J. I don't know anything about them. I assume it's going to the right and up. The omega AB is counterclockwise. Omega CE also counterclockwise. I have no idea what they're doing, and it doesn't really matter. Here are the R's that I need for the special point equations. So you can get those from before. So RAB, I think I've got that one from the other anyway. So it's 300 plus 250 from A to B, and here's your 3, 4, 5 triangle. AD, here's a 3, 4, 5 triangle. C to D, I'm using the cosine of 30. And you can do that because you're not going to differentiate the special point equations. So you execute that. So here come the special point equations. Special point equations, velocity of B equals velocity of A plus the cross product between omega and R. And then here's the second equation from between A and D, and then here's the third one between C and D. Okay? And then once you type in those equations, you say I want you to solve the special point equations, and you want to solve for the velocities, 1, 2, 3, 4, and the two angular velocities. So that's 6 terms that you want to solve for. And I just say give it to me as a number. Right? So that's what I do there. If you want to see what these special point equations look like, here they are right there. Right? So they're vectors. So VBX equals, here's the I component, here after the cross product's done. Here's the J component, and the K you would expect to be 0, right? So you expect all these Z values to be 0. So in general, you're only going to get 2 equations. You're going to get the I's over on the left-hand side. So in this case, VBX is equal to this term right here. If you really want to solve them by hand, you can. 0. Right there, the J component is equal to this piece right here. So you can pull that off and do it by hand if you want. But anyway, those are your basically 6 equations. You're going to solve for these 6 unknowns, and here's the values. And you can compare these numbers to what is found in the vector loop, and you'll find out that they're exactly the same. Okay, so it looks like I didn't do the accelerations, but the accelerations would be similar. You would just write the acceleration of B equals acceleration of A, cross, and etc. So anyway, that's how you would do special points with Mathematica. That's it.